This is the final part of the repair video, and there's a mixed result. The unit is partially fixed, but not fixed to the degree I was hoping for. Let me explain what's going on. You can see the extent of the corrosion here. You can see the extent of the corrosion. All the blue stuff is probably either an aluminum or copper oxide of some sort, and it's extensive on both sides. There you go. And the problem is that when I was doing some soldering and some desoldering, the traces were lifting off the substrate. So there were some repairs I just could not make because the circuit board was misbehaving. However, all is not lost. Right now I have 100 megahertz pumping into the 50 ohm impedance. As a matter of fact, let me take this out and put this in directly because it's terminated. Okay, I have 100 megahertz, and you'll see that we're actually getting a readout. There we go. And I'm going to dial it down to say 90 megahertz, and hello. Okay, dial it up to 110 megahertz. There we go. Dial it up to 110 megahertz. So you'll see that we're getting some signal, and it's coming through the 50 ohm high-speed interface that goes up to 600 megahertz. That's this section over here. So the 50 ohm input is this section here. This is all conditioning over here, and then we come into this 10 divider chip right over here, and this one pumps into this 74196 for another divide by 10, and then that goes through this pathway into pin 28 of the inner sill, and you'll see we have some numbers over there. So this section is working. The problem is that as I was trying to repair the high impedance input, which is used for lower frequencies below 60 megahertz, they come in this section, gets refined over here, and then comes through this line receiver chip, which is I've pulled off. No sense wasting it. This section here is beyond repair. I mean, I could start bodging up point-to-point wires, but for a cheap thing like this, when I already have other frequency counters, it's just not worth the time and effort to expend trying to make this thing work again. So I've pulled the line receiver chip. I'll use that for some other project, and I'm just going to write this section off. There was another thing I had to do, which if you look closely, right over here, let me see if I can pull that even closer. There you go. You'll see here on pin 2, you'll see a bit of solder. It turns out that the trace at the bottom of the underside of the socket for this chip, that trace was pulling off the circuit board. So even though the chip was properly nestled into the socket, pin 2 was not completing its circuit. And this is the output pin. This is where the divide by 10 signal comes out. So pin 2 is crucial. However, one lucky thing is that because that's where the signal comes out, and it goes into this capacitor, and there's a resistor in parallel right over here, I was able to bodge a little piece of wire, a little piece of 22 gauge wire from pin 2 over to the resistor to complete the circuit. So I bent out the pin and soldered directly to it. And why would I do that rather than repair the socket by putting in a new socket? Like I said, the underside of the motherboard is a mess. And the foil traces, let me get you back in focus here, the foil traces were just coming off. So I gave up on that, did this bodge, and even though it means I'll never be able to conveniently replace that chip again, frankly, if this thing needs any more repair, it's going to get trashed. I'm just going to pull out any salvageable parts and trash it. What seems to have happened is that the corrosion of the circuit board caused by the leakage of the NiCad batteries is just so extensive, and that corrosive material was on the circuit board for a matter of decades, not just years, but decades. It undermined the foil. This is not, these are not copper traces. You'll see that these traces, get you in focus, these traces are not copper colored. So these are foil traces. I don't know if they're aluminum or what, but they're foil traces, and they're just real cheap, and they pull right off the circuit board substrate. So what I'm going to do is I'm going to declare victory in as much as I have a semi-workable, semi-usable frequency meter. It's only good for high frequencies. Let me show you. I'll bring it down to 100. There we go. So it's not completely useless, but it's not fully functional either. It'll never be battery operated again. The first thing that I did find, which I do want to share with you, is that transistor that was in the orange section of the schematic, that was the final transistor where the signal was passed into pin 20 of the intersil chip, right over here. This transistor right here. Whoops, I've got to get you back in here. Okay, I'm talking about this. Where are you? There we go. This transistor right here did have to be replaced. This is the replacement transistor, and it was messy. The bottom of the transistor, the three wires from the bottom of the transistor were right here in this corner of these gang switches. So right there. And getting in there with a soldering iron and a wick of braided copper to wick away the old solder so I could replace it, that was not easy. And my desoldering gun, which is this gizmo right here, let me pull back. The desoldering gun, which does wonders, particularly on throughput, but the tip of this is just so fat that I couldn't get it in where I needed to because of those switches blocking it. So I had to do it the old-fashioned way, using a lot of flux to break down the oxides. And the flux comes as a paste like this. You might ask, well, why aren't you using rosin core flux solder? Well, I am, but the amount of flux inside the rosin core solder, where's the solder? Here's the solder, okay. The amount of flux in this solder is nowhere near sufficient to dissolve or reduce, in the chemical sense, reduce as in a reduction reaction. Remember, oxidation and reduction are the opposite of each other. So if this is all oxidation, the purpose of the flux, which is an alkali, like ammonium chloride, something like that, is to undo the oxidation. If you try and solder onto oxidized traces, the solder will not adhere, particularly because of the heat of the soldering pen tip. Heat helps oxidation. You have oxygen in the atmosphere, and when you try soldering tin or other metals with heat, that's going to accelerate the amount of oxidation. So that's why flux is important. What flux does is, if there is no oxidation, the flux prevents the oxidation from forming. In this case, where you have a lot of oxidation, you literally bathe the thing in flux. So what I do is I take a coffee stirrer and I come down, scoop up some flux, and I literally lather it on till I get a big blob. And then what you do is you solder right through the flux. You literally take the solder point and you jam it right into the flux bath, and you can solder right through it. As a matter of fact, when you do that, the soldering is much easier, and the solder goes exactly where you want it to go. Likewise, when you're using, where did it go? When you are using copper braid to remove old solder, here we go. So here's a wick of old copper braid. This is also available in Radio Shack. This stuff here wicks away old copper, but only if it's not oxidized. And even this stuff, this stuff here is 20 years old, and if you've ever tried wicking up solder using 20-year-old braid, you know it doesn't work, and that's because there's an oxide layer that forms over time on the copper braid. But you can fix that. Simply lather on or dip it in your flux, and it'll work again. Works magically. Again, because the flux is breaking down the oxide. Now, this stuff is toxic. It is really toxic. You do not want to inhale this. So I have a little fan going when I'm working with this, and the fan is sucking away the fumes of this stuff so it doesn't get into my lungs. And that's a key thing if you're ever going to use this pasty kind of flux on your projects. You want to make sure you are blowing that stuff away. It is even more potent than the flux that comes in the solder itself, because there's so much more of it. So you want to make sure you're blowing across, not up at you. You want to make sure you're blowing across the project as you're doing your soldering. Anyway, long story, a little bit shorter, was getting into this little corner was not easy, and taking out all the old solder with this stuff was not easy, but it was a lot easier when I just sticked a gigantic blob of solder of flux rather, right in there, and did the desoldering right through the flux. So that transistor, which was the common denominator of all three circuits in that orange section, that one did require changing. And then there was a on this section here, which is the high impedance section. On the high impedance lower frequency section, there's a JFET over here and a regular PNP transistor. Both of them needed to be replaced, but there was, when I was trying to replace the PNP transistor, the traces just started pulling right off, and I decided, no, that's it, we're going to stop right there before I do more damage than I fix. So this section now is a goner, and this will be useful for high frequencies. I tried getting it up to 600 megahertz, but it turns out that the chip, the 74196 chip, will not go higher than about 49 megahertz. Remember, we're dividing by 10 over here, so if I have 600 megahertz coming in here, I'm going to be feeding this chip 60. And this chip, for some reason, is not rated to 60. It's only rated to about 40, and it's doing about 46, which means that the highest frequency I can pump The highest frequency I can pump into here right now is 460 and still get numbers to show over here. So I have us at 162. Let's bring it up to 300. Here's 250. So it'll work to 250 megahertz. Let's see if we can bring it up higher. Here's 350 coming up. So it's useful to 350. Let's take it to 450 megahertz. There we go. And when I take it beyond about, let's see, let's try, here's 470, and we've already lost it. Drop it down to 460. Okay, here's 460. We're still there, but when I start going above 460, we lose it. And I figured it's either this prescaler chip that supposedly goes up to 650 megahertz, or it's the 74-196. And when I put them on the scope, it turns out that the prescaler is doing just fine. The prescaler can go much higher. I get a very good signal out of this, well beyond 460 megahertz. But right now, this is feeding, it's taking 460 in, and it's spitting out it's spitting out 46 into here. Well, when I put in more than 46 megahertz into here, this stops working. This jams up. I don't know the reason for it. It may be that this particular piece is not rated as high in frequency as the original piece that came. I had to replace the 74-196 that was in there. And this is an old piece that I had lying around from a digital clock project many years ago. So it may well be that this piece is just not rated as highly as the one that came out. But the point is, this is the bottleneck right here. So I can't go beyond 460. And the reason why I can't go beyond 460 is because, oops, I'm touching too much. Here, let me bring it down to 450 and it'll be stable again. There we go. The reason why I can't go beyond much about 450 is because of the 74-196 will not go above about 45 or 46 megahertz. I could fix that. I could solve that by simply ordering a mil-spec piece, which would go much higher, and that would solve it. However, I'm not going to do that given the context of this repair and the usefulness of this device for future projects. I have other frequency counters that go much higher, into the gigahertz now, so the usefulness of this is not all that much. The exercise was more a case of a challenge to see whether or not this could be revived after so many years before I threw it out. And I learned a lot of lessons, particularly about working on corroded boards and boards that don't have proper copper traces but have these kind of foil traces that are shit. they're just bad. So anyway, I hope you enjoyed, and this was what I was doing with my time, and I'm not sure if I'll do any more of these, but if you got any usefulness out of it, particularly in being able to interpret that schematic diagram, then it was all well worth it. Catch you later.